Today we're going to talk about a topic that we covered a bit at SmartLab in both Munich and in San Diego. But this talk is going to be a bit different and somewhat of a slight extension of that for anyone who has already heard this, this presentation. So we're calling this the evolution of the modern laboratory, how to make sense of laboratory data and drive business value from it. The reason of this is that we see laboratories as changing and evolving, specifically in regards to new kinds of technologies and technological approaches that we'll discuss today. But we also at OSTHUS look closely at how these changing landscapes affect our customers in terms of their business and how they can actually utilize these kinds of changes in new technologies to get increased value. So moving forward, we'll have a quick overview of the outline here. So we'll talk a bit about some of the current challenges with laboratory data. We'll talk a bit about data as a corporate asset and the rise of new tech. We'll talk about what is semantic technology and how can it help. We'll then talk about aligning semantic technologies with big data and analytics. And then we'll provide a vision for what we think 21st century smart labs will eventually look like. So the current challenges with lab data that exist has to do with the way that data is captured, integrated, and shared. So the top diagram there shows what we think is a common kind of desktop that we see at many of our clients, namely scientists and a lot of people around the organization. They put a lot of their information in spreadsheets and other personalized software tools that are organized on their desktop. But they're not really shareable, searchable across the enterprise, and a lot of people don't know all of the good information that exists in these people's machines. Therefore, they create personal little data silos. And aside from those personal data silos, we see that data silos get created across verticals in the organization as well. So chemists don't always talk a lot to biologists, and so on and so on. So part of the challenges we see as a big one has to do with the siloing of information, and therefore we spend a lot of time and effort with our customers talking about integration efforts and ways to overcome this. Other issues that we see, especially related to our work with the Allotrope Foundation, has to do with incompatible instruments and software systems. So some of the pictures on the bottom show just a few of these kinds of machines, like chromatography machines or HPLC machines or cell counters. There are weighing devices, mass spec machines, and so on. These things are oftentimes designed with proprietary software so that they simply can't exchange files between the various machines very easily. So you wind up with a laboratory that not only can't exchange information with other laboratories across an enterprise or with laboratories outside of the enterprise, sometimes the machinery can't even talk to each other within the same lab. Then we have problems we see with legacy architectures that are brittle and rigid. In other words, data warehouses and old database systems exist that oftentimes have to be kept alive, either for FDA reasons or because they just contain valuable data that no one wants to bother to transform or ETL into another version. Therefore, these systems are forced to live on. And we also see that SME knowledge, in other words, subject matter expertise knowledge, resides in a lot of people's heads. And very rarely do people write this kind of information down. It's just something, again, that's not very shareable across an organization. We see that data schemas are often not explicitly understood, so people use different terminologies for the same objects, or they sometimes use the same terminologies for different objects, and therefore there's a common misunderstanding and a lack of vocabularies. And we also see a lack of common vision between a lot of the business units and the scientists themselves. So sometimes the people at one level of the organization, specifically at the executive level, are not always in lockstep with people who are doing a lot of the more basic work and the labs are aligned with. So Alexander now is going to basically ask a quick poll before we go any further. I'll hand the microphone over to him.
Thank you, Eric. So our first poll for today is, how would you rate these challenges at your company? And you may vote now. Give you about a minute, and then we show the results for everyone. Okay, thank you very much. Eric, what do you think regarding the results of this poll?
I think it's interesting. So I'm noticing no one is claiming that these problems are solved, but that there's a fairly close number of people who claim that similar challenges either exist or that they're addressing the challenges already, which is good. So I'd be curious when we get through this if people in the question and answer period have any comments or any kinds of specific questions on how well this aligns, what we're going to say, how well it aligns with what their current challenges are and how they're meeting those challenges. Okay. So moving on. This slide just represents a picture of a lot of times what we see in pharma in action. In other words, we see a lot of data systems where some person, the person here in the middle of the diagram, basically has to reach out into systems themselves or reach out to other people who have to reach into disparate systems in order to pull back information, compile it, compose it, and then submit it for some type of either validation testing or perhaps regulatory affairs reporting or something like this. So when we see this type of scenario, when we've seen this in the past, oftentimes what we attempt to do is to remove some of these barriers by applying semantic technologies and other types of technologies where we can more easily integrate directly all of these different kinds of data sources and therefore allow people a type of access via web services or whatever right to their desktops or their laptops or their tablets or whatever in order to remove these kinds of bottlenecks. So this is an example of a past client of mine where this process of producing a report from all of these sources took 5 to 6 weeks to complete. Oftentimes because it had to be redone over and over and over because of lack of communication or because of missing data or people not being able to get the queries done in time or whatever. But this system, the system that we built for this specific customer who was in medical device, we were able to move that 5 to 6 weeks down to 12 to 40 seconds and also remove almost all of the errors out of any of these reports. So it pretty much ran at 100% efficiency. If we ask then why data matters, it's really because data is becoming a company's most valuable asset. So even potentially above your products themselves, the ability to track products, to know customer satisfaction, to profile use, and to derive new kinds of products out of existing ones is really important. And so what we see in the marketplace and what we agree with has been pointed out, for example, by people at Forrester and Gartner who say, for example, big data and analytics investments alone aren't enough to drive positive business outcomes. In other words, you need to identify the right technologies to fit your pain points. So we oftentimes hear people tell us that they've spent a lot of money on building a new data lake, or they've put some type of new analytics system in place, and the software was very expensive, and they're simply not seeing a lot of good results out of it. And it's oftentimes because those technologies were not actually put in place with the end result of solving a certain set of problems in mind. The other quote that you see on the top right-hand side comes out of Gartner all the way back really from 2012. And it's that understanding the business drivers, therefore, is as important as picking out the latest technology trend. In other words, the content is really king. So Andrew White, a long time ago, said, good ideas don't just come out of the woodwork or spring forth from a data mart. So I find this to be kind of an interesting convergence of opinions on these topics. And you'll see others who do work in this kind of space, who do a lot of management consulting, saying the same types of things. So, for example, if you look at this slide, this question immediately pops up to mind when I see something like this as which technology is the right one for your needs? So I borrowed this from Tom Flaherty's webinar that he put out. It was actually a conference presentation, but I think it shows some very interesting areas of the technology here. So we see data analysis platforms, we see data warehousing and databases, we see business intelligence systems, we see some of the new key value stores or big data kinds of databases, object databases, XML databases, and so on. So the question is, you know, out of this plethora of technology, do you actually know what all of these things do and which ones really fit your need? Or are people just going off and buying something because, well, I heard that this technology or that technology was good? So if we look then at what we're talking about, analytics and data science really for the 21st century has to do with integrating a lot of really complex items. So we all know that the size of data sources continue to grow. Most people have seen the statistic that says 90 to 92% of the world's data has been created in the last couple of years. There are continuously growing user groups of different types within organizations. And then answers need to reflect these increasingly complex patterns because you have more and more data and different user groups putting it in with different perspectives. So the complexity of the pattern solving is continuing to grow as well. So the rate of change in digital information we also see growing exponentially. So cloud computing, we would argue, is now fairly critical for scaling any enterprise. New data types are often being created that hold significant value, and data is also becoming more personalized and more context-based. So the effect of data that's changing the business landscape is very interesting because back in 2008, a PR Newswire article came out that basically said approximately $900 billion a year is lost on lowered employee productivity and reduced innovation from information overload. In other words, by giving people all of this information, giving them all of this data and all of this access, you would expect that we would do a better job. And in fact, people are finding out that many workers suffer from analysis paralysis, if you will, and have reduced productivity and reduced innovation because they simply can't sift through the amount of data that they now have. And the quotes on the bottom from McKinsey back in 2011 are pretty prophetic and have pretty much come true. They claimed that back then that increasing volume and detail of enterprise information, multimedia, social media, and the Internet of Things will fuel exponential growth in data for the foreseeable future. We see that happening all the time. And the use of big data will become a key basis of competition and growth for individual firms. So therefore, those who get it right are going to have a competitive advantage. Those who get it wrong could be behind the curve. All right, so how do we address some of those problems? I mean, we probably all know and read these kinds of articles, so we're aware of these issues. But one of the things we'd like to talk about here in this webinar is how we think semantic technologies in specific can help. But first, we're going to go through briefly what they are, because I think there's a lot of confusion around these technologies, and our goal here is to try and remove some of that mystification of what these things are. So we see semantics as having high value, and that's because the way that people discuss things, the way that we communicate, is itself a very interesting kind of technique. So semantic technologies it shouldn't surprise anyone, actually has its origins in philosophy. It's generally understood as the abstract study of meaning, and it's distinguished from syntax. So semantics and syntax are not the same thing. Syntax are the things that are a rule-based grammar of some language, and that could be the grammar of English, the grammar of German, the grammar of Cantonese, the grammar of Python or XML or some type of codified language. But really what we're trying to get at in our data these days is we're trying to get to the meaning. We're trying to get to the content. So if we look at a word, for example, like Washington, it can have a lot of contextual baggage with it. We can mean a president. We can mean a city, which is a capital city in the United States. We can mean the state, which is on the complete opposite side of the country from the city. We can mean a bridge that connects basically Manhattan to other parts of New York City. We can talk about a football team with a contested logo. We can talk about other individuals named Washington who are not presidents, but some who are, for example, football players for the New York Jets. And we can talk about a baseball team in Washington, for example. And normally when we have these conversations, we understand if the context is about people or places at least, or objects like bridges or sports teams or presidents. But computer systems, of course, can't do this well. So we have to explicitly explain these kinds of entities and relationships in models. So hence enters the push to the semantic web. And what we see with the semantic web, Tim Berners-Lee's vision coming true to the point of where we now have a lot of intelligent information, and a lot of that information is integrated in ways behind the scenes such that you can now intelligently search for objects. Google uses semantics to give you rich snippets and so on. But if we look back at the history, we see that from 1945 until 1970, the code was actually more important than the data. So this was back in the age of Turing machines and punch cards and things. The way that you actually structured the data was more important than what the data was about. Then in the 70s, you had this turn towards relational models and databases. And here the data became as important as the code. Now you have schemas. And then in the late 90s, as semantics started to grow, you see now that we've risen or evolved to a level where the data is now more important than the code. So what your data is about is more important than whether your data is in a SQL database or whether you have it represented in some kind of XML schema or whether it's in Python or whether it doesn't really matter now what language it's in. You're trying again to get at that meaning. So semantics has helped move this discussion further along. And what we see, therefore, is the use of taxonomies. And we see an increase in the amount of people who are looking for reference data management. Because you have all of this meaning and all of this structure now, people want to put this structure into some type of graphical or some type of organized way. So we see taxonomies as providing an important structure to data because they form these nice acyclical tree graphs. There are basically two ways that you can build taxonomies. One captures subclass and superclass relationships, which is what is shown in these pictures here, or other ones capture broad, narrow relationships between terms, which is like the tag cloud up in the top right. In other words, that's sort of a WordNet approach where I say, well, I have a term such as taxonomy, and it has some connection to ranking and to formal and to whatever. But the idea here is that you can start to structure your data in a logical way that helps to make sense of what these semantic terms mean. So we do some work with the Allotrope Foundation. Anyone who's interested in this topic, I'm not going to go into it, but you can go to www.allotrope.org. And you can see that there is a large consortium that is growing between around a dozen or more pharma and biotech companies who have decided to start pooling their instrument data and their laboratory data. They want to have an exchange format so that these instruments can start to talk to one another and they can start to more easily move data around and share it. So in the Allotrope Foundation, we have 4 basic taxonomic areas. We have equipment, we have materials, we have processes, which are completely temporal things, and then we have these information objects or results, which are basically data entities. So they're not real things like materials and equipment are. They're the outcome of some process that produced some piece of data or information. So what you see in Allotrope is this capability now to share information across laboratories and to share information across individuals, because we're painstakingly moving through these various types of taxonomic processes and getting the vocabulary and the terms straight, and then organizing them around some of these principles. So oftentimes we get asked, well, what's the difference between just doing a taxonomy and doing an ontology? And the answer in a really simplistic sense is that ontologies are basically connected taxonomies. Taxonomies only connect to one another via subclass, superclass relationships. So if you look at these 3 colored taxonomies, you could easily organize your spatial regions, your plants, and your insects, but they share no relationship to each other. So if I want to say, for example, that Florida has trees called lemon trees, and that lemon trees have a certain kind of pest that eats them called a leaf miner, then I draw those relationships trans-taxonomically. I want a deeper kind of relationship than just saying that Florida is a state and state is a spatial region, or well, a lemon tree is a citrus tree and a citrus tree is a type of plant, and so on. I want to start to make some new kinds of connections. I want to make deeper statements in my modeling. And when I connect these taxonomies this way, I start building graphs. And as soon as I start building graphs, then what I'm able to do is I'm able to add more and more logic to my models, and I'm able to structure more and more semantic content. So oftentimes what we do is we begin with code that are basic lists of things. We pull out terms, so you may pull out things like soil, plant, compound, drug, country code, location, lab, personnel, whatever. We put those into a controlled vocabulary, which means now we have agreed upon terms. We give them specific labels that subject matter experts approve. We structure them then taxonomically, so we put them in a hierarchy to say which things are bigger classes that contain other classes underneath them. From there, we can build thesauri, so now we give things a preferred label, so we can say, well, the preferred label for this country is a number, but it can have alternate labels, like it could be called Germany or Deutschland or whatever it is that you would also like to call it. And then when you go for when you build queries against this data, you get not only the preferred label, but you can also get all the alternate labels of the synonyms along with it. From there, we move to RDF models. I'll explain that in a moment. RDF is basically the resource description framework, which is a W3C standard for building these kinds of graphs and capturing your data as graphs. All your data now gets turned into triples, so you have these subject, predicate, object relationships. And from RDF then, when we traverse that red line, now we move into deeper semantics, and we get into OWL ontologies, where we add axioms and we start to add logical constraints and rules and things, all the way over to reasoning, where now, based on these rule-based logics, we can actually discover new entities, discover new relationships, and discover new patterns in our data. So what's the business value of all of this? I mean, it sounds like interesting technology. A lot of people talk about it. Semantics can model data really at many levels, really at almost any level that you can describe. So we can have semantic models that model business drivers. We can have semantic models that model your master data, the stuff that's really critical to your organization. We can have semantic models that, of course, model your reference data. That's what it should be doing at base level. And we can also have semantic models that can even capture lower level data. And data from various levels can then be integrated together through types of domains. So the way that you can integrate your plant data with your pest data with your pesticide product data is by having these various domains and drawing the logical relationships between them. And then this way you can build end-to-end logical models across an entire enterprise. And schema levels in this approach, what's very interesting, are separated from the data levels. And the business value of this is that, first of all, data becomes much more flexible and reusable. The models can be changed, the models can be reused. They simply map down to the low-level data sources because you give everything a URI where it's located. And therefore, it allows easier transformation of data to real knowledge creation. So now I can actually go in and find new kinds of information that might not exist in my raw data, and it raises the computational value. Now my data can be more easily extracted from my legacy systems. I can share it. I can use it across the enterprise. And one of the big things here is because there's no more point-to-point data mapping, I don't have to worry about tearing the whole system down and having to remap all of these data tables individually to one another. I make the mappings from my data tables to my model, and once that's done, very few things often change at the model level. If things do change at the model level, you have just a couple of mappings to remap, and there's logic internal to these systems that will actually tell you if you've broken a mapping, if you have an inconsistency, or if something is wrong. So the point-to-point data mapping problem is one that in the long term has really cost people a lot of money over the years in terms of retooling their databases. So the benefits of semantic technology then that we see are you get interoperability, you get improved searching and browsing, you get better reuse of your data from your models, and you can also go find ones that exist out on the web. You can also capture architectural intent. So unlike database schemas where the intent of the schema is often buried in the schema, here you supply definitions, you can write down annotations, you can see who built this thing, when they built it. They can put a whole bunch of comments in about why they structured it this way. So architectural intent is often a big thing because as you start sharing these things across an enterprise, different people who can come to this technology can understand how and why it was built. You can then apply automated reasoning, which is really nice because you can remove a lot of steps and you can remove a lot of querying, and you get a nice development life cycle for your products in the end. All right, so we're going to switch gears a little bit now and talk about aligning semantic technologies with some big data and analytics, because we don't just do semantics to do semantics, we do semantics to find answers. And there's a lot of other technologies that have grown up in the past few years that are non-semantic, but are very, very interesting and very, very useful. Specifically things in big data analytics that utilize new kinds of NoSQL databases or mathematical approaches to graph theory where you deal with probabilities and uncertainty in the data. So the first thing I'll say about this is this is a borrowed concept from Craig Roth's 2012 Gartner paper that I found really interesting. And there they talk about the move from big data to big content. And so big content was first introduced by Craig in 2012. And he said that big content combines technologies to go beyond traditional search to text analytics, sentiment analysis, video analysis, semantic web technologies, and attention management. So big content stresses more what your data is about and who it and basically who is using it to make certain informed decisions. So the move to big content shows a natural evolution of combining technologies such as semantic tech with analytics. And in fact, where this really took hold was in targeted marketing and advertising campaigns. So a lot of companies started to realize it's not just about shoving all of our data into these massive data warehouses, because remember, even though we're giving people more and more data, they may not actually be able to innovate or use it very well. So The idea of big content is about let's give people data with some kind of meaning behind it so that they can actually utilize this data. They can find the patterns in it that make sense to them. And again, this is more about personalizing things for people. So let's explore these concepts a little bit further. So the rise of analytics is really changing the game. This is a slide that I use in my cloud computing class at NYU. And I find this really interesting. The statistics in here come from a book called Race Against the Machine. And basically, the idea is this. The power of analytics is just now beginning to be felt. So for the longest time, we worried about Moore's Law. And Moore's Law said, well, look, given the amount of data we have, processing speed has to double every so many years to keep up. And people thought, oh my, how are we ever going to keep up with all this processing that needs to occur? But actually, as the authors of this book point out, that if you look at the growth of analysis and not the growth of processing, you'll see that between 1988 and 2003, computer processing speed grew by 1,000x. But in the same period, algorithm development grew by 43,000x. So algorithms are growing at a rate of 43 to 1 to processing speed. So what does this tell you about the direction in which we're headed? Well, to give you an idea of what these authors talk about and what some other folks like Ray Kurzweil have shown, is they call this problem the second half of the chessboard problem. So there's a very old mythical story. Some date it back to ancient China, some date it back to parts of Europe. Doesn't matter. The bottom line is that this story goes like this. A peasant went to the emperor, and the emperor asked this person to do a task for them. And when the peasant person agreed, the emperor said, what do you want in payment? And he said, well, really simply, take your chessboard out and put 1 grain of rice on the first black square in the lower left-hand corner. And then just double that grain of rice every square along the chessboard. So 1 becomes 2, 2 to 4, 4 to 8, 8 to 16, and so on. So the emperor, of course, looking at the chessboard, thought, okay, well, this is great. I'm going to get off really inexpensively to do this task. But actually what happens is when you get to the second half of the chessboard, what you find is that this exponential growth becomes really, really big. In fact, when you get to the final square of the chessboard, as you can see, it's 2 to the 63rd power. So what you wind up with in terms of rice, and this story is supposed to be back in 400 BC or something like this. This person basically would have had to get would have been paid 461 billion metric tons of rice, which is 1,000 times the global production of rice in 2010. So what this means is that the second half of the chessboard, you see this really huge exponential growth in size. So people who talk about analytics and who talk about big data say, we are kind of now getting to that yellow line, that tipping point, and moving even beyond it perhaps a bit, where the size of the data now, because of social media and other feeds, is starting to grow so exponentially that we really need to understand new ways to pull the content out of it, to understand it. Therefore, we need our algorithms to grow and to mature at the same kind of rate, or we'll just have too much data and not be able to really process the information we need. So, understanding the big V's of data, we'll cover 4 of them here. The 4 V's of big data that we normally talk about, and I've seen as many as 9 in some people's work, but we stick with the basic 4, the first ones. You have volume, you have velocity, you have variety, and you have veracity. So volume is basically the amount of data you have. Velocity is how fast you can either move it around, move parts of it around, or query against it and get results. And that's really where a majority of big data analytics approaches sit. So most of the companies that are actually talking about big data analytics, that's the focus. Semantic technologies, however, really apply well to the variety piece, because the complexity of the data is increasing, and therefore the model complexity continues to increase as well. And you get a lot of different types of data where having good reference sources and having good metadata and models around that becomes really, really key to success. The last piece, veracity, is actually where semantics falls apart. And this is one of the reasons why I'm saying we have to move from semantics and combine with other types of technology, because the veracity piece has to do with uncertainty of data. It's data that's in doubt. So we don't always have a clear image of what's going on in our data. It's incomplete, it's uncertain, and so on. So mathematical techniques for clustering, for kernel density algorithms, for these other kinds of approaches, there's many, many kinds of algorithms that you can build that can statistically help you with the veracity problem. But the question is, how do you bring that together with the variety problem? And that's where we're going to go next. But first, I'm going to turn it back over real quick to Alexander, who has another quick poll for the audience here. So Alexander, are you still there?
So our second poll is about how big of a challenge is big data analytics for your company? Again, I will stop it at about 1 minute, and then we have a look on the results. Okay, no more new votes are coming in. So at the moment, we've got for 66% of our audience, it's a large challenge, and for all others who voted, it's a medium challenge. I'll hand over to you.
Thanks. So that's interesting. That tells me that people are worried about the amount of data that they have. And one of the things, even as a card-carrying semantics person, that I'll say is that semantics is not really the appropriate technology to handle those kinds of challenges, which is why we're talking about some of these other areas. But if we look at why does semantics matter then for data analytics? Because for a long time, people had said, well, logic-based systems and ontologies work one way, and math-based systems and statistics work completely differently. So therefore, you can't really bridge those two. You can't really bring them together. We at OSTHUS disagree. We see that semantics as a reference data and as a structuring and organizing set of principles actually can help improve statistical data analytics. So we see that big data approaches require a lot of proper metadata and terminologies to integrate the information well. So most of these algorithms run on some type of a classifier. And the question is, what do your classifiers mean? Are your classifiers used the same way across different algorithms? Are they used the same way in your organization? The things that you're measuring, when you find clusters, the question is a cluster of what, right? What is it that you're talking about? Because as we all know, statistics can be used to show X or not X, oftentimes with equal aplomb or efficiency. The other thing is that the relationships really matter in the data. Part of my postdoctoral graduate career was spent in the field of data fusion. And in this field, we did some work and published some fairly significant papers at the University of Buffalo showing what we termed at the time ontologically enhanced stochastic graph matching. And that's a big mouthful for saying we're using ontology models with nodes and arcs in them to augment these statistical graphs that get built out of the data. So you may have a statistical graph that comes up and has a node of person. And if you have a node of person in your statistical graph and you merge it with an ontology graph, an ontology is going to tell you all these other attributes and related classes of persons. Persons have birth dates. They have ID numbers that are normally singular. They can have things like passports. They have addresses. They own objects. They all come from parents. So there's all this other information the ontology can bring to your nodes of your statistical graph to help enhance and improve that graph. And oftentimes then when you're doing statistical matching, you get improved results in terms of how good of a job those matching algorithms are doing. The third thing is that you can really understand perspective and context. That's crucial for success in today's world and in today's data, because as we said, the data is getting more complex, the models are getting more complex, and it's really important that you have good context. And then the fourth part is that semantics provide really better data models and schemas that allow people, again, to look at a lot of the variety of the data and to really look at what is the application, who are the people that are using this, and what are you attempting to do. So we're just about running out of time now. We wanted to go about 45 minutes and have some time for some questions. So we're going to end by simply giving a quick vision of what we see moving forward for some of the customers that we're currently working with. We see smart labs for the 21st century looking much differently than labs look right now. I believe that hybrid technologies, basically using things like semantic tech plus statistical analysis for big data and for big data analytics applications, will reshape the future of laboratories. We see that this type of hybrid approach is going to allow us in that second half of the chessboard to really bring together more information and allow better crunching across it and give you better big content analysis ultimately. I think therefore that 21st century labs in the future are going to provide their customers with the following things. So if you think back on the first slide, this is kind of the opposite of those challenges that currently exist. They're going to provide you with integrated data, so you'll have a common reference structure, common vocabularies, common terms. And for terms that you can't decide on, or someone says, well, no, I don't agree completely with that term, that's fine. You're going to have synonyms, or you're going to have relationships to other terms and other domains, or say, well, in this context, these people use this term. In this context, they use that term. It's not about making people speak the same language and use the same words. It's about giving them the ability to communicate and to at least understand and explicitly state what these things mean and how they stand. You're going to have shareable data. You're going to have easier interaction across teams and across business units. So you're going to see an improvement in things like regulatory reporting. You're going to see an improvement in things like pre-competitive laboratory cross-company interactions and working. You're going to see an improvement in scalability because big data applications in cloud can be set up in these virtual machines that are highly elastic. One of the arguments I've made for a long time is that I think semantic technologies was hampered because people tried to do everything in these graphs, but we simply couldn't get enough memory behind them to be successful. Cloud grew up right next to the semantics world, and now if you say, well, if I take my model and I can run that in a cloud application, I have lots of elasticity and a lot of scalability that I can utilize now to actually make my semantic system perform better than they had historically done. You're going to get conceptual representations, so you're going to get business context and perspectives that are captured. So now you're going to see a better fit between the business drivers, for example, at major pharma companies, the things that they're trying to do, the new products they're trying to roll out, the continuous improvement perhaps in QA, QC testing, and so on. And you're going to see a linkage of those drivers to the actual data coming out of the labs. So we think that that with these kinds of conceptual representations, you're going to actually see the gap narrowing between the scientists doing the work and the business leaders that are driving the companies. And we also think that you're going to see advanced analytics. You're going to get complex and automated problem-solving capabilities. People are going to have information pushed to them. It's going to look more like the Internet of Things. You're going to have more information just provided to you right at your fingertips. Systems will be doing a lot of the basic brute force, block and tackle type of activities. No longer will people just be getting a huge sea of information being, and told to, query to their heart's content. This is going to be about advanced analytics. This is going to find analysis that matters to you and your team, analysis that matters for this specific project. And you're going to have the reuse of items to be able to do analyses across different types of areas in laboratory spaces. So we see the future as very interesting, very bright, and something that we think is going to really be a game changer moving forward. So I thank everybody very much for attending and for listening, and we're going to take some comments now. Alexander will serve as moderator. So if anyone has any comments or questions, you can feel free to type them in the chat, and we'll get to them.
Thank you, Eric. So in between, we already had a few questions. During the semantics and ontologies topics, the question was asked, how could someone who's interested in this try this out as a prototype?
Okay, if I understand you, if someone is interested in semantics, how would you try it out as a prototype?
Yes.
Well, so there's a couple things you can do. Number one, you can download a free copy of Protégé, which is a piece of software from Stanford University that came out of Mark Muson's lab. And you can start to mess around with organizing your data semantically. There are some tutorials online, like the pizza ontology and the wine ontology, that will help teach you some basics of ontological classification and using OWL and RDF. But what I always recommend to people is that if you are really interested in this kind of technology and you're thinking about toe dipping a bit and doing a type of examination or proof of concept, it's oftentimes really good to go have a small training session with some experts in this field. So there's Semantic Arts, Dave McComb's people do a nice training, the Top Quadrant people do training. It's mostly on their tool. I believe the Cambridge Semantics guys, at least they used to do some training stuff. We at OSTHUS do training. The idea is that if you bring in someone to talk to you about these high-level concepts, they will not only bring these concepts in, but they'll actually link those concepts to some small piece of your data, making it very relevant for you, and then can help you actually to formulate a proof of concept that can give you a quick win. So the one thing I would stress not to do is don't go tackle a huge problem and don't go build some large sets of ontologies and try to solve some complex area of your business and model those kinds of things, because there are tricks to doing this and it gets very complicated very fast. And so some of us, myself included, we've tripped over some of the tripwires already, so we know where they are and we know how to avoid them. My recommendation is to play around with a tool, look at some of the available technology and some of the items out there. You can visit the World Wide Web Consortium. There's lots of information up there on, for example, how to write Sparkle and such. But if you're really not that technical or you don't really want to dive in to that degree, find someone to come in and do a semantic training for a day or two. And I think you'll find that you'll get some really nice direction from them.
We've got another question. Can you give a specific example on how you would integrate data?
Yeah, sure. Well, first of all, it depends what kind of data it is. But I'll assume that you mean legacy data. So if there's legacy data, normally what we do is we come in and we look at the data source that's there. We look at the structure it's in. Is it in a database? Is it structured like in some kind of SQL or Oracle database, Postgres, what have you? So in other words, is it tables with columns and rows and these kinds of things, or is it semi-structured data? Is it things that are maybe Excel sheets that's somewhat structured, but also has cells that has some text or some other items in it, or images or pictures or something? Or is it highly unstructured? Is it a lot of text and you're trying to do keyword searches, or you're trying to mine concepts out of free text? So the type of data you have really matters. But regardless, if I'm integrating something, and let's take a system that has all three. I would start by, I'd look at the data schemas of the relational tables, and you can convert those schemas relatively easily and quickly into RDF OWL. So tables can be classes, columns can be attributes, rows can be instances. That's a very quick and dirty way to do it. Oftentimes that's not quite good enough. You have to actually look at what some of these things mean. And then you have some of the items in there like primary foreign key relationships to deal with and so on. But you basically start by modeling, by building a generic model around those data structures. So you like to use the data sources that are there, but oftentimes you have to augment them with some human kinds of concepts that aren't necessarily in the database themselves. Moving to the semi-structured stuff, again, you can often, there are tools out there and techniques that allow you to go right from a spreadsheet into an RDF OWL representation of that, so into a graph. Again, you want to make sure that your relational tables and your vocabularies are aligned with your spreadsheet or your semi-structured vocabularies and models that you're building. And then for the unstructured part, normally you start with something like a natural language processing tool of whatever level you would like. So some people, frequency co-location of words is enough. For other people, they want deep linguistic capabilities. You use those tools to pull out your terms. You populate your models with those terms. And again, you align your classes across your structured, semi-structured, and unstructured data sources. That class structure now has layers to it. So there'll be a very, very upper layer, and you can choose from several out there. So there's Sumo, Buffo, Dolce, and several other ones. We at OSTHUS tend to work closely with a lot of the Buffo, BFO, basic formal ontology, upper ontology constructs, but we use a light version of it, so we don't need all that machinery. But if you build your upper level ontology, this is going to give you your spatial things, your temporal things, your information entity things, and so on. And underneath that, then you're going to build some mid-level classes of, whatever your data is about. If it's about compounds, if it's about crude oils, if it's about manufacturing processes or financial data or whatever, you need to figure out the level of specificity that you want this middle tier of ontology classes to be about, and then you're going to link those classes down to those raw data sources that you've basically connected via the mappings, via that modeling step I talked about in the first place. So it's fairly complicated, but you can do large-scale integration in this way. And then, of course, you have the querying capability to query your model using Sparkle, which is the Sparkle query language. It's a recursive definition, but using Sparkle, there are techniques where Sparkle will actually translate into SQL, for example, and go hit your database for the instance level data. The Sparkle is simply used for your class and attribute level data. So one of the things I didn't mention is this idea that one of the values here is that you separate the model layer out from your data layer.